You wouldn't notice it happening. No flash of light, no sudden movement, no moment you could point to and say, it begins here. What's unfolding is quiet, patient, almost invisible. In the universe, not everything is born in violence or fire. Some of its most important transformations happen slowly, across thousands, millions, sometimes billions of years. Matter drifts. Gravity whispers. Time does the rest. This is a story about slow creation, about change that happens so gradually it feels like stillness, so slow that a human lifetime is far too short to witness it. Take a deep breath. Let your thoughts drift. Let's begin in a planetary nebula, one of the most beautiful and peaceful sights in the cosmos. Despite the name, planetary nebulae have nothing to do with planets. They're called that because when early astronomers first saw them through telescopes, their round, disc-like shapes reminded them of planets. But they're actually something far more magnificent, the outer layers of dying stars gently expelled into space. Imagine a star like our Sun about 5 billion years from now. It has spent billions of years steadily fusing hydrogen into helium in its core, shining peacefully, providing light and warmth to any planets that might orbit it. But eventually, the hydrogen in the core runs out. The core contracts under its own gravity and heats up. The outer layers of the star expand, swelling outward until the star becomes a red giant, perhaps 100 times larger than it was before. For a few 100 million years, the star continues in this swollen state, fusing helium into carbon and oxygen in its core. But this too eventually ends. Without fusion to support it, the core contracts into a dense white dwarf, while the outer layers, no longer gravitationally bound to the core, begin to drift away into space. Not explosively, not in a violent supernova, but gently, calmly, expanding outward at perhaps 20 or 30 kilometers per second. This expanding shell of gas is illuminated by ultraviolet light from the hot white dwarf at its center, causing it to glow in beautiful colors. Hydrogen emits red light. Oxygen emits green and blue. Nitrogen emits red. The result is a glowing bubble of gas, delicate and ethereal, expanding slowly into the darkness of space. From our perspective, watching through telescopes from Earth, these nebulae appear frozen, static, unchanging. But they're moving, growing, evolving. They're just doing it so slowly that we can't see the change in a human lifetime. The Ring Nebula, visible through small telescopes in the constellation Lyra, has been expanding for about 6,000 years. It's roughly 1 light year across now and will continue to expand for tens of thousands of years more before gradually fading as the gas disperses and becomes too thin to glow. The Helix Nebula, one of the closest planetary nebulae to Earth at about 700 light years away, looks like a giant cosmic eye staring back at us, peaceful and calm. Its gas expanding gently outward from the white dwarf at its center. These nebulae represent the end stage of most stars' lives, the peaceful conclusion of billions of years of steady burning. They're not violent or chaotic. They're serene, beautiful, the universe's way of recycling material, returning the elements created inside stars back to the interstellar medium where they can eventually form new stars and planets. The atoms in your body passed through a nebula like this at some point, expelled from a star that died billions of years ago, drifting through space until they were incorporated into the cloud that formed our solar system. Let's drift now from these glowing bubbles to another peaceful phenomenon, the slow rotation of pulsars. Pulsars are neutron stars, the collapsed cores of massive stars that exploded as supernova. They're incredibly dense, about 20 kilometers in diameter, but containing more mass than the Sun. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. These objects spin rapidly, some completing hundreds of rotations per second, and they emit beams of radiation from their magnetic poles. As the pulsar rotates, these beams sweep across space like a lighthouse beam, and if Earth happens to lie in the path of the beam, we detect regular pulses, hence the name pulsar. But not all pulsars spin rapidly. Some rotate much more slowly, taking seconds or even minutes to complete one rotation. These slow pulsars are often older, having gradually slowed down over millions of years as they lose rotational energy to the radiation they emit. There's something deeply calming about imagining these ancient, slowly rotating stellar remnants, patient and steady, marking time with their regular pulses, cosmic clocks that have been ticking for millions or billions of years. The slowest pulsar known rotates once every 24 seconds. Imagine that. A star collapsed to the size of a city, spinning so that one rotation takes nearly half a minute. From our perspective, we'd see a pulse of radio waves every 24 seconds, regular as clockwork, unchanging, reliable. This pulsar has probably been rotating for millions of years, gradually slowing, and it will continue for millions more, a patient cosmic timekeeper in the vast darkness of space. Pulsars are so regular that they can be used as cosmic clocks. Astronomers have timed pulsar pulses with such precision that they can detect tiny variations caused by gravitational waves passing through space or by planets orbiting the pulsar. The regularity of pulsars is one of the most stable phenomena known in nature, rivaling the best atomic clocks we can build on Earth. There's something profoundly peaceful about that constancy, that reliability in a universe that often seems chaotic and random. Let's move now to an even calmer phenomenon, the orbital motion of planets around distant stars. Not hot Jupiters whipping around their stars every few days, but distant, cold planets in slow, stately orbits far from their suns. Imagine a planet like Neptune orbiting a star similar to our Sun at a distance of 30 astronomical units, taking about 165 years to complete one orbit. From the planet's perspective, the stars are fixed points of light that barely move. The Sun is a bright star, brighter than any other, but still small and distant, providing only faint warmth and light. The planet drifts through its orbit so slowly that over a human lifetime it would move only a small fraction of the way around its star. Everything is patient here, unhurried, operating on timescales that dwarf human experience. This planet might have moons, small icy worlds orbiting the planet just as the planet orbits its star. These moons trace their own paths, slower and more stable even than the planet itself in some ways. A moon orbiting far from a Neptune-like planet might take hundreds of days to complete one orbit, cycling through phases as seen from the planet's cloud tops, waxing and waning in the dim sunlight. There's no life on this cold, distant world, no observers to mark the passage of time, no one to notice the slow drift of the seasons as the planet's tilted axis causes different hemispheres to receive slightly more or less of the faint sunlight over the course of its long year. But the planet doesn't need observers. It simply exists, orbiting, following the laws of gravity, tracing out an ellipse in space that it has traced countless times before and will trace countless times again. Throughout the galaxy, there are billions of such planets, cold and distant, orbiting their stars in peaceful isolation, following their appointed paths through space, undisturbed and undisturbing. They represent the majority of planets in the universe, not the dramatic hot worlds close to their stars, not the potentially habitable worlds in temperate zones, but the cold outer planets, the ice giants and frozen super-Earths, drifting through the darkness, patient and serene. From these distant planets, let's journey to an even more tranquil realm, the spaces between galaxies, the cosmic voids where almost nothing exists. Galaxies are not evenly distributed through space. They cluster together, forming groups and clusters and superclusters, connected by filaments of galaxies stretching across hundreds of millions of light years. And between these structures lie voids, vast empty regions where very few galaxies exist. These voids are enormous. The Boat's void, one of the largest known, is about 330 million light-years in diameter and contains only about 60 galaxies, compared to the thousands or millions you'd expect in a similar volume of space elsewhere. Imagine floating in such a void, impossibly far from anything. In every direction for hundreds of millions of light years there would be almost nothing. A few dim, distant galaxies, so far away they're barely visible as faint smudges of light, but mostly just darkness and emptiness. This emptiness is not a true vacuum. Even in the voids there's still some gas, some dark matter, some radiation. The cosmic microwave background, the afterglow of the Big Bang, fills even the emptiest regions of space with faint microwave photons. But by any standard we're familiar with, voids are about as close to nothing as the universe gets. They're peaceful in the most profound way, not just quiet, but nearly absent of phenomena altogether. And yet, even in the voids, things happen, just very slowly. The few galaxies that exist there drift through space under the influence of gravity. The universe expands, carrying them farther apart. Dark energy, the mysterious force causing cosmic expansion to accelerate, operates here just as it does everywhere else, gently pushing space apart, making the void slightly larger over time. On Earth, we're surrounded by matter and energy and constant activity. But in the voids, an observer would experience the universe in its most minimal state. It's a profound kind of peace, the peace of near-nothingness, of space stretching on and on, with almost nothing to disturb it. And there's something calming about knowing that such places exist, regions of the cosmos where quietness and emptiness reign, where nothing much happens and nothing needs to happen. Let's return now from the emptiness of voids to something gentler and more structured, the slow dance of binary stars. About half of all stars in the galaxy exist in binary or multiple star systems, orbiting around their common center of mass. Some binaries are close, with the stars whipping around each other in hours or days, but others are distant, with orbital periods measured in years, decades, centuries, or even millennia. Imagine two sun-like stars separated by about 50 astronomical units, roughly the distance from our sun to the Kuiper belt. They orbit their common center of mass once every several hundred years. From the perspective of a planet orbiting one of these stars, the companion star would appear as an extremely bright point of light, much brighter than any planet, but still just a star, not a sun. It would move very slowly across the sky, taking human lifetimes to trace out its apparent path as the two stars orbit each other. For an observer on such a planet, the companion star would be a permanent fixture in the night sky, slowly moving, slowly changing its position relative to the background stars, a reminder that their sun is not alone, but part of a bound system, two stars linked by gravity, orbiting together through space. The gravitational dance is eternal, or as close to eternal as anything in the universe gets. As long as the stars exist, they'll continue their orbit, bound together, companions through the vast darkness. Some binary systems are even more separated, with stars orbiting thousands of astronomical units apart, taking tens of thousands or even hundreds of thousands of years to complete one orbit. These are the most peaceful binaries, where the orbital motion is so slow that countless generations could observe the system without detecting any change in the stars' positions relative to each other. The stars are companions in the truest sense, sharing space and gravitationally linked, but so distant from each other that they barely affect each other's evolution or environment. These systems remind us that orbital motion, the phenomenon that governs everything from moons around planets to galaxies around each other, operates at all scales and timescales. It's one of the most fundamental processes in the universe. Objects moving in response to gravity, following paths determined by mass and distance and velocity. And it's peaceful, orderly, predictable. We can calculate orbits millions of years into the future with great accuracy because the mathematics of gravity is so well understood and because gravitational interactions are so stable and regular. From binary stars, let's drift to an even gentler phenomenon, the slow migration of stars through the galaxy. Stars are not fixed in space. They move orbiting the galactic center, along with billions of other stars. Our Sun, for example, orbits the center of the Milky Way once every 230 million years or so, moving at about 230 kilometers per second relative to the galactic center. But stars don't all orbit in perfect circles. Their orbits are slightly elliptical, and they bob up and down through the galactic disk as they orbit, crossing through the midplane every few tens of millions of years. These motions are imperceptibly slow from a human perspective, but over millions of years, they carry stars through different regions of the galaxy, exposing them to different environments, different densities of gas and dust, different rates of supernova explosions nearby. The Sun's nearest stellar neighbors are constantly changing as stars move through the galaxy on their independent orbits. About 70,000 years ago, a small red dwarf star called Scholz's star passed within about 1 light-year of the Sun. Closer than any known star has come since. In about 1.4 million years, the star Gliese 710 will pass even closer, within about 10,000 astronomical units, possibly disturbing comets in the Oort cloud and sending some of them toward the inner solar system. But these close approaches are rare. Most of the time, the Sun drifts peacefully through its region of the galaxy, far from any other stars, accompanied by its planets and comets and asteroids, a small island of matter and the vast emptiness between stars. The nearest stars are light years away, so distant that their light takes years to reach us, so distant that they exert no meaningful gravitational influence on the solar system. This isolation is typical for stars. Despite there being hundreds of billions of stars in the galaxy, space is so vast that stars are generally very far from their neighbors. The average distance between stars in our region of the galaxy is about 5 light years. That means if you could travel at the speed of light, it would take 5 years on average to get from one star to the next. And of course, nothing can travel at the speed of light except light itself, so the journey would take much longer for any physical spacecraft. This vast separation between stars means that stellar interactions are rare and gentle. Stars don't collide or pass close to each other very often. They drift through the galaxy on their separate paths, occasionally influencing each other gravitationally if they pass relatively close, but mostly existing in isolation, independent systems following their own trajectories through space and time. There's something profoundly peaceful about this stellar solitude. Each star is its own world, or rather its own system of worlds if it has planets, operating according to the same physical laws as every other star, but doing so independently, in its own corner of space, disturbed only rarely by external influences. The sun has been shining for 4.5 billion years in this peaceful isolation, and it will continue for another 5 billion years or so, a stable, steady presence in an otherwise empty region of space. Let's consider now one of the most calming aspects of the cosmos, the constancy of physical laws. Throughout the universe, as far as we can tell, the same laws of physics operate. Gravity works the same way in distant galaxies as it does here. Light travels at the same speed everywhere. Atoms have the same properties. Fundamental constants like the gravitational constant, the speed of light, the charge of an electron, these appear to be the same throughout the observable universe and throughout cosmic time. This constancy provides a kind of cosmic stability. The universe might be vast and ancient and full of phenomena we don't fully understand, but it's not arbitrary or chaotic. It follows rules, and those rules are mathematical, expressible in equations that we can write down and solve. This makes the universe comprehensible in principle, even if many specific details remain unknown. Consider the law of gravity. Newton expressed it as a force proportional to the product of two masses, and inversely proportional to the square of the distance between them. Einstein refined it in general relativity, showing that gravity is actually the curvature of space-time caused by mass and energy. But in either formulation, gravity is consistent and predictable. We can calculate the orbit of a planet millions of years into the future, and if we have accurate enough measurements of its current position and velocity, our calculation will be correct. This predictability extends to other physical laws as well. The way atoms emit and absorb light follows quantum mechanical rules that we understand. The rate of radioactive decay follows statistical laws that are remarkably precise. The expansion of the universe follows equations derived from general relativity. All of these phenomena are governed by laws, not by chance or whim, and those laws appear to be universal and unchanging. There's something deeply reassuring about this. The universe could have been chaotic, with different rules in different places or at different times, making it impossible to understand or predict. But it's not. It's orderly. It has structure and pattern, and that order and structure make it possible for complexity to exist, for stars and galaxies and planets, and eventually life to emerge and persist. The constancy of physical laws also means that the universe has been predictable throughout its history. The processes that formed the first stars 13 billion years ago were governed by the same laws that govern star formation today. The orbits of planets in the early solar system followed the same gravitational laws that govern planetary orbits now. This continuity connects the present to the past and the future. We're part of a continuous cosmic story, governed by the same fundamental rules that have operated since the beginning. From the constancy of laws, let's turn to another peaceful phenomenon, the patient process of stellar evolution. Stars don't change quickly. They evolve over millions or billions of years, spending most of their lives in stable equilibrium, fusing hydrogen into helium, shining steadily. The Sun has been doing this for 4.5 billion years, and will continue for another 5 billion or so. During all that time, its properties have changed only gradually. It's slightly brighter now than when it formed, and it will gradually brighten further as it ages. But the changes are slow enough that they're barely noticeable over timescales of millions of years. This stellar stability is what makes life possible. If stars changed rapidly, if their brightness and temperature fluctuated wildly, planets orbiting them would experience dramatic climate changes that would make it difficult for complex life to evolve and persist. But stars are stable, at least during their main sequence lifetimes, and this stability provides a constant source of energy for any planets that orbit in the habitable zone where conditions might be right for life. Even when stars do change, the changes are generally gradual. When a Sun-like star exhausts the hydrogen in its core, it doesn't explode or die instantly. Instead, it gradually expands over millions of years, becoming a red giant. It might remain in this red giant phase for a few 100 million years before eventually shedding its outer layers as a planetary nebula. The timescales are vast, patient, unhurried. Only the most massive stars end their lives violently, exploding as supernovae when they can no longer sustain fusion in their cores. But even these stars spend millions of years in stable states before the final explosion. And supernovae themselves, while violent, are also in some sense peaceful, because they're part of the natural cycle of stellar evolution. They're not disasters or anomalies. They're expected endpoints for massive stars, playing an essential role in enriching the galaxy with heavy elements and triggering new rounds of star formation. After a supernova, the expelled material expands outward as a supernova remnant, mixing with the interstellar medium, providing the raw material from which future stars will form. The Crab Nebula, the remnant of a supernova observed in 1054 CE, is still expanding today, nearly 1,000 years later, its glowing filaments stretching across about 11 light-years of space. It's a beautiful object, chaotic in appearance, but peaceful in its steady expansion, a reminder that even violent events in the cosmos eventually give way to quieter phases. Let's drift now to consider one of the most subtle and pervasive phenomena in the cosmos, the expansion of space itself. The universe is expanding, which means that galaxies are moving away from each other as space stretches between them. This isn't motion through space, but the expansion of space itself, carrying galaxies along with it. And the expansion is accelerating, driven by dark energy, a mysterious component that makes up about 68% of the universe's total energy. This expansion happens everywhere, but it's only noticeable on very large scales. Within galaxies, gravity is strong enough to hold matter together, despite the expansion. The Milky Way isn't expanding. The solar system isn't expanding. Even the space between stars and the galaxy isn't expanding in any meaningful way. But on scales of millions or billions of light years, the expansion becomes apparent. Distant galaxies are receding from us, and the farther away they are, the faster they recede. The expansion is gentle and gradual. The Hubble constant, which describes the rate of expansion, is about 70 kilometers per second per megaparsec. That means for every megaparsec of distance, about 3.3 million light years, galaxies are receding at an additional 70 kilometers per second. This might sound fast, but on cosmic scales it's actually quite slow. It takes billions of years for the expansion to significantly change the distances between galaxy clusters. There's something profoundly peaceful about cosmic expansion. It's been happening for 13.8 billion years since the Big Bang, and it will continue forever if current understanding is correct. It's not something we need to worry about or react to. It's just a background process, the universe gradually growing larger, space stretching, galaxies moving apart. And it's so slow that it will never directly affect human life or even life on Earth. By the time the expansion has any noticeable effect on the local universe, the Sun will have long since become a red giant and made Earth uninhabitable. The expansion also means the universe has a horizon, a limit to how far we can see. Light from very distant galaxies has been traveling toward us for billions of years, and during that time the expansion of space has stretched the light to longer wavelengths, shifting it toward the red end of the spectrum. The most distant galaxies we can see are so far away that their light has been traveling for over 13 billion years, showing us what those galaxies looked like when the universe was young. But there are galaxies even farther away, beyond our cosmic horizon, whose light hasn't had time to reach us yet and never will, because they're receding faster than light can travel through the expanding space between us. These galaxies are forever beyond our view, part of the universe but inaccessible to observation. There's something mysteriously peaceful about that, knowing there are realms of existence we can never observe, regions of the cosmos that will remain forever unknown to us. From cosmic expansion, let's turn to another peaceful phenomenon, the existence of rogue planets, worlds that drift through interstellar space unbound to any star. These planets were either ejected from their star systems through gravitational interactions or formed independently in interstellar space. They wander through the galaxy alone, not orbiting any star, following their own paths through space. Imagine such a planet, perhaps Jupiter-sized, drifting through the darkness between stars. No sun illuminates it. No parent star provides warmth. It's heated only by the slow release of gravitational energy from its formation, and possibly by radioactive decay in its core. Its surface or cloud tops are frigid, perhaps only a few dozen degrees above absolute zero. If it has moons, they orbit in perpetual night, never seeing a sunrise because there's no sun. This planet has been drifting for millions or billions of years, perhaps since shortly after the galaxy formed. It's traveled vast distances, possibly tens of thousands of light years, passing through different regions of the Milky Way, but its journey is lonely and uneventful. It doesn't interact with anything. It just drifts, pulled slowly by the collective gravity of the galaxy, following an orbit around the galactic center, just like stars do, but doing so in isolation, unaccompanied, alone. There may be billions or even trillions of rogue planets in the galaxy, outnumbering stars. They're extremely difficult to detect because they don't emit much light and they're not near any stars that would illuminate them. Occasionally, we detect them through gravitational microlensing, when they pass in front of a more distant star and briefly magnify its light through their gravitational field. But mostly they remain invisible, hidden in the vast darkness between stars. These planets represent a kind of ultimate peace, existence without companionship, without external influence, without even light. They simply are, drifting through space, following the laws of gravity, patient and eternal in their solitude. There's something profoundly calming about contemplating these lonely worlds, knowing they exist out there in the darkness, peaceful and undisturbed, going nowhere in particular, just existing. Let's consider now one of the most ancient phenomena we can observe, the cosmic microwave background, the afterglow of the Big Bang. About 380,000 years after the universe began, it had cooled enough for electrons to combine with protons and form the first neutral hydrogen atoms. Before this, the universe was opaque, filled with a hot plasma of charged particles that scattered light. But once neutral atoms formed, the universe became transparent, and light could travel freely through space. This light, emitted from every point in the early universe, has been traveling ever since. Over the intervening 13.8 billion years, the expansion of the universe has stretched these photons from visible light to microwave wavelengths. Today, this radiation fills all of space with a nearly uniform glow at a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. We can detect this radiation with sensitive instruments, mapping it across the sky. It's remarkably uniform, varying by only about 1 part in 100,000 from place to place. These tiny variations represent density fluctuations in the early universe, the seeds that eventually grew into galaxies and galaxy clusters. But the overall uniformity is what's striking. The universe was incredibly smooth shortly after the Big Bang, and that smoothness is preserved in the cosmic microwave background. There's something deeply peaceful about this ancient light. It's been traveling for almost the entire history of the universe, crossing billions of light years of space, and it's still here, detectable. A permanent reminder of cosmic origins. Every cubic centimeter of space contains about 400 photons from the cosmic microwave background. They're everywhere, passing through you right now, mostly undetected and unnoticed, but present, a subtle connection to the beginning of everything. The cosmic microwave background is also a kind of ultimate limit to observation. We can't see anything from earlier times because the universe was opaque before the radiation was emitted. This light represents our deepest view into the past, the earliest epoch we can directly observe. Beyond it lies the dark ages of the universe, a period we can study only indirectly through theoretical models and observations of its consequences. But within this limit, the cosmic microwave background provides an extraordinary snapshot of the early universe, showing us what conditions were like when the cosmos was young and simple, before stars and galaxies had formed, before complexity had emerged. It's a peaceful image, a nearly uniform sea of radiation, marking the transition from opacity to transparency, from plasma to neutral atoms, from simplicity to the gradual emergence of structure. Let's turn now to one of the most mysterious and yet peaceful components of the universe, dark matter. Dark matter makes up about 85% of all matter, but it doesn't emit, absorb, or reflect light, which is why we call it dark. We know it exists because of its gravitational effects on galaxies and galaxy clusters, but we don't know what it's made of. It's one of the great unsolved mysteries in physics. But from another perspective, dark matter is incredibly peaceful. Unlike ordinary matter, which can interact through electromagnetism and the nuclear forces, dark matter interacts only through gravity and possibly the weak nuclear force. This means dark matter particles pass through each other and through ordinary matter without colliding or interacting in any significant way. Dark matter doesn't clump together to form dense objects like stars or planets. It doesn't heat up through friction or pressure. It just drifts through space, forming vast halos around galaxies, providing the gravity that holds those galaxies together. Right now, dark matter particles are passing through you. Billions of them every second, moving at hundreds of kilometers per second, going right through your body, through Earth, through everything without interacting at all. You don't notice them because they don't affect ordinary matter except through their extremely weak gravitational pull, which is negligible on human scales. This ghost-like quality of dark matter makes it profoundly peaceful. It's everywhere, making up most of the matter in the universe, but it doesn't disturb anything. It doesn't cause explosions or collisions or chaos. It just provides gravity, gently holding galaxies together, shaping the large-scale structure of the universe, doing its job quietly and invisibly. Scientists are trying to detect dark matter directly by building sensitive detectors deep underground, hoping to catch the rare occasion when a dark matter particle interacts with an atomic nucleus in the detector. So far, these searches have found nothing definitive, which tells us that dark matter is even more elusive than we thought. But the search continues, and perhaps someday we'll identify what dark matter actually is, solving one of the deepest mysteries in cosmology. From dark matter, let's drift to another peaceful phenomenon, the slow but steady nuclear fusion occurring in the cores of stars. This is the process that powers stars, converting hydrogen into helium and releasing energy in the form of light and heat. In the sun's core, about 600 million tons of hydrogen are fused into helium every second, and in the process about 4 million tons of mass are converted into pure energy according to Einstein's equation, E equals mc squared. This might sound violent, but it's actually a remarkably gentle process. Fusion in the sun's core occurs at a rate that keeps the sun stable. The outward pressure from the energy released by fusion exactly balances the inward pull of gravity, maintaining equilibrium. This balance has been maintained for 4.5 billion years and will continue for another 5 billion, a testament to the stability of stellar fusion. The fusion process itself happens gradually. Individual protons in the sun's core rarely collide with enough energy to fuse. The core is hot, about 15 million degrees Celsius, but even at these temperatures, fusion is rare for any given proton. A proton in the sun's core will wait, on average, about 9 billion years before it fuses with another proton. That's longer than the current age of the universe. And yet, because there are so many protons in the sun's core, about 10 to the 56th of them, fusion events happen constantly. Trillions upon trillions of fusion reactions occur every second, releasing the energy that eventually makes its way to the sun's surface and radiates into space as sunlight. It's a beautiful example of how individual rare events can sum to a substantial collective phenomenon when you have astronomical numbers of participants. This steady fusion is what makes the sun reliable. It doesn't flicker or vary wildly in brightness. It shines steadily, providing a constant source of energy for Earth and any other planets in the solar system. This constancy is essential for life. If the sun's output varied significantly, Earth's climate would fluctuate dramatically, making it difficult for life to evolve and persist. But the sun is stable, and that stability creates the conditions for life. Let's contemplate now one of the most profoundly peaceful facts about the cosmos: its sheer age and the vastness of cosmic time. The universe is 13.8 billion years old. That's a span of time so vast it's almost impossible to comprehend. Human civilization has existed for about 10,000 years. Modern humans have existed for about 300,000 years. Life on Earth has existed for about 4 billion years. But the universe is more than 3 times older than Earth itself. This means that most of cosmic history occurred before our solar system even formed. Stars were being born and dying, galaxies were forming and colliding, the universe was expanding and evolving, all of this happening for billions of years before Earth existed. And Earth's entire history, from its formation to the present day, is just the last third of cosmic time. Looking forward, the universe has an even longer future ahead of it. If current cosmological models are correct, the universe will continue expanding forever. Star formation will continue for perhaps 1 trillion years or more, gradually slowing as the available gas is exhausted. White dwarfs, the remnants of sun-like stars, will cool slowly over trillions of years. Black holes will evaporate through Hawking radiation over timescales of 10 to the 100 power years or more. These timescales are so vast they're almost meaningless. 1 trillion years is 1,000 times longer than the current age of the universe. 10 to the 100 years is a 1 followed by 100 zeros, an incomprehensibly large number. And yet the universe will persist through all this time, following the laws of physics, evolving, changing, but never ending. There's something deeply peaceful about this cosmic patience. The universe is not in a hurry. It has all the time in the world, literally. Processes that seem impossibly slow to us, like the evaporation of black holes or the cooling of white dwarfs, are just part of the natural progression of cosmic evolution, no more rushed or delayed than anything else. Time extends endlessly forward and backward from this present moment, and we occupy just an infinitesimal slice of it, a brief flicker of consciousness in the vast span of cosmic time. This perspective can be both humbling and liberating. Humbling because it shows how small and brief we are. Liberating because it suggests that our anxieties and concerns, real as they are to us, are temporary and insignificant on cosmic scales. The universe has been here for billions of years and will be here for trillions more. Our lives are brief, but they're part of this vast story, connected to everything that came before and everything that will come after. Let's consider now one final peaceful phenomenon, perhaps the most fundamental of all, the existence of the universe itself, the fact that there is something rather than nothing. This is not a question science can easily answer. Physics tells us how the universe behaves, how it evolved from the Big Bang to the present, how stars form and galaxies evolve and planets orbit. But it can't tell us why there's a universe at all, why existence exists. Some physicists have tried to show how a universe could arise from nothing through quantum fluctuations, how the laws of quantum mechanics allow for the spontaneous creation of particles and even entire universes. But this just pushes the question back. Why are there laws of quantum mechanics? Why is there anything rather than nothing? These are philosophical questions, perhaps unanswerable, but they're worth contemplating. The universe exists. You exist. Consciousness exists. These facts are remarkable regardless of whether we can explain why they're true. Perhaps existence is simply a brute fact, something that requires no further explanation. Perhaps asking why there's something rather than nothing is like asking what's north of the North Pole, a question that seems meaningful but actually isn't. Let's spend more time exploring peaceful cosmic phenomena, discovering the gentle rhythms and calm processes that make the universe not just vast and powerful, but also serene and beautiful in ways we rarely contemplate. Consider the ancient light journeying through space. Every photon of light we receive from distant stars and galaxies has been traveling for years, centuries, millennia, or even billions of years. The light you see from the Andromeda Galaxy, our nearest large galactic neighbor, left that galaxy 2.5 million years ago, when human ancestors were still learning to make stone tools. The light from more distant galaxies has been traveling far longer, crossing billions of light years of expanding space to finally arrive at your telescope or camera. These photons have experienced an extraordinary journey. They traveled in straight lines through the near vacuum of intergalactic space, undisturbed by anything, moving at the speed of light, the cosmic speed limit. They passed through regions of space that expanded during their journey, stretching their wavelengths, shifting them toward redder colors. Some might have been gravitationally lensed by massive galaxy clusters, bent around these concentrations of matter, taking a curved path through space-time. And now, after this incredible voyage lasting millions or billions of years, some of these photons enter your eye or strike a detector, and we learn about the distant sources that emitted them. We can analyze the light's spectrum and determine what elements exist in that distant star or galaxy. We can measure its redshift and calculate how far away it is and how fast it's receding. Each photon is a messenger from the distant past, carrying information across cosmic distances and cosmic time. There's something profoundly peaceful about this. The photons don't struggle or strain. They simply travel, moving through space at constant speed, following the geodesics of curved spacetime, patient and eternal in their journey. Whether they're eventually absorbed by something or continue traveling forever through expanding space, they simply exist and move, requiring nothing, disturbing nothing, just being and traveling. Let's contemplate the peaceful process of molecular cloud collapse and star formation, but at a pace that emphasizes its gradual, gentle nature. Molecular clouds are vast regions of space filled with cold hydrogen gas and dust. They're called molecular because the hydrogen exists as H molecules rather than individual atoms. These clouds can be hundreds of light years across and contain enough material to form thousands or even millions of stars. But the process is slow. A molecular cloud might exist for millions of years in a relatively stable state, with internal turbulence and magnetic fields providing support against gravitational collapse. But eventually, perhaps triggered by a shock wave from a nearby supernova, or simply through gradual cooling and loss of support, a portion of the cloud begins to collapse. Even the collapse is slow by human standards. The gas falls inward under its own gravity, but the process takes hundreds of thousands of years. As it collapses, the cloud fragments into smaller pieces, each collapsing independently, forming a cluster of protostars. These protostars continue to accrete material from the surrounding cloud, growing slowly over time, heating up as gravitational energy is converted to thermal energy. Eventually, after perhaps 1 million years of collapse and accretion, the core of a protostar becomes hot and dense enough for nuclear fusion to begin. Hydrogen starts fusing into helium, releasing energy, creating outward pressure that halts the collapse. The star has reached the main sequence and will now shine steadily for millions or billions of years, depending on its mass. The entire process from the initial collapse to the arrival on the main sequence takes a few million years, which seems like a long time but is actually quite brief in cosmic terms. And yet, during that time, nothing dramatic happens. Just gas slowly falling inward, density gradually increasing, temperature slowly rising, until finally fusion ignites and a new star is born. It's a gentle genesis, unrushed and patient, the universe taking its time to create a new light in the darkness. Let's turn our attention to the quiet depths of space between stars within a galaxy. This interstellar medium, as it's called, is not empty. It contains gas, mostly hydrogen, with some helium and trace amounts of heavier elements, along with tiny dust grains made of silicates and carbonaceous materials. But it's incredibly diffuse. In the densest regions, molecular clouds, there might be a few thousand atoms per cubic centimeter. In more typical regions, there might be only 1 atom per cubic centimeter or less. For comparison, the air you're breathing contains about 10 to the 19th atoms per cubic centimeter. That's 10 billion atoms in a volume the size of a sugar cube. The interstellar medium is vastly more empty, closer to a vacuum than anything we can create on Earth. And yet this diffuse gas is the raw material from which stars and planets form. It's the repository for material ejected by dying stars. It's where cosmic rays travel, where magnetic fields thread through space, where chemistry happens on the surfaces of dust grains. There's something peaceful about the interstellar medium's emptiness. It's not hostile or threatening. It's just space, mostly empty, occasionally punctuated by atoms and dust grains, patient and quiet, waiting to be gathered by gravity into future generations of stars. You could travel through it for light years without encountering much of anything, just occasional atoms, photons of starlight, cosmic rays, magnetic fields, the faint glow of the cosmic microwave background. This emptiness is typical of the universe. Despite all the stars and galaxies, most of space is nearly empty. The universe is mostly vacuum, with matter concentrated into small regions where gravity has pulled it together. This makes space peaceful in a profound way. There's so much room, so much emptiness, that most of the cosmos is quiet and undisturbed, a vast arena where occasionally interesting things happen, but mostly nothing happens at all. Let's consider the peaceful phenomenon of tidal locking, where a moon or planet's rotation period matches its orbital period, causing it to always show the same face to the object it orbits. Our moon is tidally locked to Earth, which is why we always see the same side of the moon from Earth. The far side, often incorrectly called the dark side, is never visible from our planet. Tidal locking occurs because of tidal forces, the difference in gravitational pull on the near and far sides of an object. Over time, these forces create internal friction that dissipates energy, gradually slowing the object's rotation until it matches its orbital period. Once locked, the configuration is stable, and the object remains locked unless some external force disturbs it. Many moons in the solar system are tidally locked to their planets. The Galilean moons of Jupiter are all tidally locked, always showing the same face to Jupiter. Most of Saturn's moons are locked as well. Even some binary star systems can become tidally locked to each other, with each star always showing the same face to its companion. There's something profoundly calm about tidal locking. Once achieved, it's a stable equilibrium that can last billions of years. The locked object doesn't struggle or change. It simply orbits, rotating at exactly the rate needed to keep the same face toward its parent. A perfect synchronization maintained by the subtle influence of tidal forces. It's an example of the universe finding stable configurations and settling into them, patient and content to remain in that state indefinitely. From tidal locking, let's drift to the peaceful radiation of black-body objects. A black body is an idealized object that absorbs all radiation that falls on it and emits radiation based solely on its temperature. While perfect black bodies don't exist, many objects in nature approximate black body behavior, including stars, planets, and even the cosmic microwave background. The radiation emitted by a black body follows a specific spectrum called the Planck spectrum, which depends only on temperature. Hot objects emit more radiation at shorter wavelengths, appearing blue or white. Cooler objects emit more at longer wavelengths, appearing red or even invisible in infrared. The Sun, with a surface temperature of about 5,700 Kelvin, emits most of its radiation in visible wavelengths, which is why it appears yellow-white to our eyes. But many objects in space are much cooler and emit primarily in infrared. Brown dwarfs, failed stars that never achieve sustained fusion, might have surface temperatures of only a few hundred Kelvin and emit mostly infrared radiation. Rogue planets drifting through interstellar space might be even cooler, barely warmer than the cosmic microwave background, emitting faint infrared glow from residual heat. There's something peaceful about black body radiation. It's not explosive or violent. Objects simply emit photons at a rate determined by their temperature, steadily, constantly, gradually cooling as they radiate energy into space. It's a gentle process, universal and unchanging, governed by the laws of thermodynamics and quantum mechanics. Every object in the universe emits thermal radiation unless it's at absolute zero, and nothing in the universe is quite that cold. Even you are emitting black body radiation right now, primarily in infrared wavelengths, because your body temperature is about 310 Kelvin. This radiation carries away the excess heat your metabolism produces, helping maintain your body temperature. It's a constant, gentle process, invisible to your eyes but essential to your survival, and it connects you to every other warm object in the universe. All of us radiating, all of us slowly exchanging energy with our surroundings. Let's contemplate the ancient globular clusters, spherical collections of hundreds of thousands of old stars orbiting in the halos of galaxies. These clusters formed early in the history of galaxies, perhaps more than 10 billion years ago, and they've been orbiting ever since, slowly moving through the galactic halo, occasionally passing near the galactic disk, but mostly remaining in the outer regions. The stars in globular clusters are old, red, and dim compared to young stars. They've been burning for billions of years, slowly converting hydrogen to helium, gradually cooling and fading. They're packed relatively close together compared to stars and galactic disks, separated by only a few light weeks or light months on average. This might sound close, but it's still vast by human standards. If the Sun were in a globular cluster, the nearest stars would be hundreds of times closer than in our current location, but they'd still be so far away that their light would take weeks to reach us. These old stars orbit the cluster's center of mass in a complex gravitational dance, their motions determined by the collective gravity of all the stars in the cluster. Over billions of years, close encounters between stars can eject some stars from the cluster, gradually dispersing it. But this process is very slow, and many globular clusters have survived largely intact for the entire history of the galaxy. There's something peaceful about these ancient clusters, these collections of old stars that have been together for billions of years, orbiting their galaxy, slowly evolving but enduring. They're like cosmic fossils, remnants from the early universe, survivors from an era when galaxies were young and star formation was more vigorous. They remind us that not everything in the cosmos changes rapidly, that some structures can persist for almost the entire age of the universe. Let's consider the gentle process of accretion, where material gradually falls onto an object, adding to its mass. This happens in many contexts in astronomy. Planets form through accretion, with dust grains sticking together to form pebbles, pebbles forming boulders, boulders forming planetesimals, and planetesimals eventually merging to form planets. Stars form through accretion, with gas falling from a surrounding disk onto a growing protostar. Even black holes grow through accretion, with material spiraling inward through an accretion disk before crossing the event horizon. Accretion can be violent in some cases, particularly around black holes where material heats to millions of degrees and emits X-rays, but in many cases it's gentle and gradual. A protoplanetary disk around a young star might accrete onto the star at a rate of only a few millionths of a solar mass per year, a slow trickle of material falling inward. This accretion continues for millions of years, gradually adding to the star's mass and affecting its evolution. Even after planets have formed, accretion continues at a much reduced rate. Earth is still accreting material, gaining about 40,000 tons per year from meteoroids and cosmic dust falling through the atmosphere. This might sound like a lot, but it's utterly negligible compared to Earth's total mass of about 6 times 10 to the 24th kilograms. At the current rate, it would take trillions of years to significantly increase Earth's mass through accretion. This ongoing but minimal accretion is peaceful and constant. Every day, dust from space, remnants from comets and asteroids, falls through Earth's atmosphere. Most burns up as meteors, creating brief streaks of light. Some reaches the ground as micrometeorites. It's a subtle connection between Earth and space, a gentle reminder that we're part of the solar system, constantly interacting with it, even if the interaction is minimal. From accretion, let's drift to the calm persistence of magnetic fields in space. Magnetic fields are invisible but pervasive, threading through planets, stars, galaxies, and even the intergalactic medium. Earth has a magnetic field generated by currents in its liquid iron outer core. This field extends into space, creating the magnetosphere that protects us from solar wind and cosmic rays. The sun has a magnetic field that becomes twisted and tangled by the sun's differential rotation, creating sunspots and solar flares and coronal mass ejections. But between these active events, the sun's magnetic field is relatively calm, slowly evolving, gradually changing configuration over the 11-year solar cycle. Galaxies have magnetic fields too, generated by currents in interstellar plasma and amplified by dynamo processes similar to those in planets and stars. These galactic magnetic fields are weak, only a few millionths of a Gauss, far weaker than a refrigerator magnet, but they extend across vast distances, threading through the entire galactic disk and halo, influencing the motion of charged particles and affecting processes like star formation and cosmic ray propagation. There's something peaceful about these magnetic fields and visible structures that permeate space, gently influencing charged particles, shaping the flow of plasma, creating order in the chaos. They don't attract attention the way luminous objects like stars and galaxies do, but they're essential components of the cosmos, part of the underlying structure that makes the universe work the way it does. Let's contemplate the peaceful coexistence of matter and antimatter annihilation in the early universe. In the first moments after the Big Bang, the universe was hot enough that particles and antiparticles were constantly being created and destroyed. Photons with enough energy could spontaneously convert into particle-antiparticle pairs, and these pairs would quickly annihilate back into photons. The universe was in thermal equilibrium, with creation and annihilation balanced. But as the universe expanded and cooled, photons no longer had enough energy to create particle-antiparticle pairs. The annihilation continued, but creation stopped. If particles and antiparticles had been exactly equal in number, they would have completely annihilated, leaving only photons. But for reasons we don't fully understand, there was a slight asymmetry, about one extra matter particle for every billion particle-antiparticle pairs. When the annihilation ended, this tiny excess of matter remained. That excess is everything we see in the universe today. All the stars, galaxies, planets, and everything on them, including you. We're made from the leftover matter that survived the great annihilation, the 1 in a billion surplus that didn't find an antiparticle partner. This is a peaceful thought in a strange way. The universe could have been left empty, just photons with no matter at all. But a tiny asymmetry meant that matter survived and over billions of years. That matter organized itself into stars and galaxies, and eventually into structures complex enough to support life and consciousness. We're the descendants of that primordial asymmetry, the beneficiaries of a cosmic imbalance that occurred in the first second of the universe. From asymmetry, let's turn to the peaceful darkness that dominates most wavelengths of light in space. When we look at the night sky with our eyes, we see stars, bright points against darkness. But this is misleading. Space is actually filled with light at wavelengths we can't see. Infrared, microwave, radio, ultraviolet, X-rays, gamma rays. If we could see all these wavelengths, space would appear much brighter, filled with glowing gas, shining galaxies, and energetic phenomena. But most of space is still dark at most wavelengths. The universe is transparent to most light, which means photons can travel enormous distances without being absorbed or scattered. This transparency is what allows us to see distant galaxies and observe the cosmic microwave background. If space were opaque, filled with absorbing material, we'd only be able to see nearby objects. The darkness of space, its transparency, is essential for astronomy and for understanding the universe. It's also profoundly peaceful. Space doesn't obstruct or obscure. It allows light to pass freely, carrying information from distant sources to observers anywhere. This openness, this lack of barrier or interference, makes the cosmos observable and comprehensible. Let's contemplate now the peaceful process of crystallization in space. Crystals form when atoms or molecules arrange themselves in regular, repeating patterns. On Earth, we're familiar with crystals like salt, sugar, diamonds, and snowflakes. But crystallization happens in space too, in contexts very different from anything on Earth. In the cold molecular clouds where stars form, dust grains can accumulate mantles of ice, with water, methane, and ammonia molecules freezing onto the grain surfaces and forming crystalline structures. In the atmospheres of cool stars, microscopic crystals of minerals like silicon carbide and aluminum oxide can condense, forming the dust that will later be ejected into space and contribute to the interstellar medium. In the cores of white dwarfs, the extremely dense matter can crystallize, with carbon atoms arranging themselves into a giant cosmic diamond. The process takes billions of years as the white dwarf slowly cools, but eventually the entire interior might solidify into crystalline form, a diamond star hiding beneath a thin atmosphere of hydrogen or helium. There's something deeply peaceful about crystallization, about atoms finding their lowest energy configuration and settling into it, creating order and pattern from disorder and randomness. It happens slowly, patiently, requiring nothing but time and the right conditions. And once formed, crystals are stable, maintaining their structure unless disturbed by external forces. Let's consider the calm diffusion of elements through the universe. Every element heavier than hydrogen and helium was created inside stars either through fusion during the star's lifetime or in supernova explosions when massive stars die. These elements are expelled into space, mixing with the interstellar medium, gradually enriching it with heavier elements. Over billions of years, this enrichment has changed the composition of galaxies. The first stars formed from primordial gas containing only hydrogen and helium. But these stars created heavier elements and dispersed them when they died. Second-generation stars formed from gas that included these heavy elements, and they created even more. Each generation has slightly higher metallicity, meaning a higher fraction of elements heavier than helium. Our Sun is a third-generation star or later, formed from gas that had already been enriched by earlier stellar generations. The Earth and everything on it, including you, is made from this enriched material, from atoms created in stars that died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was synthesized in stellar cores and scattered into space, eventually finding its way into the molecular cloud that formed the solar system. This cycle of synthesis, dispersal, and incorporation is peaceful and continuous. Elements flow from stars into space, from space into new stars and planets, and eventually perhaps back into space again when those stars and planets end. It's a cosmic recycling program operating on timescales of billions of years, ensuring that the universe gradually becomes more chemically diverse and complex. And this brings us full circle, back to where we began, contemplating the peaceful processes and gentle phenomena that characterize so much of the universe. From expanding nebulae to slowly rotating pulsars, from distant planets in lazy orbits to the patient expansion of space itself, the cosmos is full of calm, unhurried processes that unfold over vast timescales, requiring nothing from us except observation and appreciation. Let me share with you a few more serene cosmic stories, gentle observations about the universe that remind us of its underlying tranquility beneath all the apparent drama and energy. Think about the loneliness of light. Every photon, every particle of light travels alone through space. Photons don't interact with each other under normal circumstances. Two beams of light can cross paths without affecting each other at all. A photon emitted from a distant star travels through space in isolation, never encountering another photon from that star, moving in its own straight line through the curved geometry of space-time. This solitary journey can last billions of years. The photon doesn't experience time or distance, a strange consequence of relativity. From the photon's perspective, if such a thing could be said to exist, its emission and absorption happen simultaneously, with no time passing between them. But from our perspective, the photon's journey spans billions of years and billions of light years of space. Eventually, that photon might encounter something, a dust grain that absorbs it, a gas atom that scatters it, a detector on Earth that records its arrival. After its long, lonely journey, the photon's existence ends in an interaction, its energy transferred to whatever absorbed it. It's a peaceful end to a patient voyage, a conclusion that was inevitable from the moment the photon was emitted. Consider the invisible neutrinos, ghostly particles that barely interact with matter. Neutrinos are created in nuclear reactions, including the fusion reactions powering the sun. Trillions of neutrinos pass through your body every second, coming from the sun, from other stars, from cosmic rays interacting with Earth's atmosphere, from radioactive decay in the Earth. They pass through you, through Earth, through almost everything, without interacting, without being stopped or slowed. Neutrinos are so weakly interacting that a neutrino could pass through a light year of lead without being absorbed. Most neutrinos from the sun pass right through Earth as if it weren't there. Occasionally, very rarely, a neutrino will interact with an atom, and we can detect this interaction with sensitive detectors. But most neutrinos travel through the universe forever, never interacting with anything, eternal ghosts moving at nearly the speed of light. There's something profoundly peaceful about neutrinos. They're everywhere, constantly streaming through space and matter, yet they disturb nothing. They're like witnesses to the universe, passing through events without affecting them, observing without interfering. They carry information from deep inside the sun, from the cores of collapsing stars, from the early universe, but they share that information only rarely, only when they happen to interact with a detector designed to catch them. Let's contemplate the slow changes in orbital configurations within planetary systems. Orbits are not perfectly stable over extremely long timescales. Gravitational interactions between planets, though weak, accumulate over millions and billions of years, gradually changing orbital parameters. Eccentricities can increase or decrease. Inclinations can change. In rare cases, planets can even be ejected from their systems through gravitational interactions. But these changes happen so slowly that they're imperceptible on human timescales. The solar system is about 4.5 billion years old, and the current orbital configuration of the planets is roughly what it was 1 billion years ago, and roughly what it will be 1 billion years from now. Small changes accumulate, but the overall structure remains stable. This is why we can calculate planetary positions thousands of years into the future or past with high accuracy. This long-term stability is what makes planetary systems habitable. If orbital configurations changed rapidly, planets would experience dramatic climate variations as their distance from the sun changed. Earth's relatively circular orbit, which varies only slightly over hundreds of thousands of years, is part of what makes our climate stable enough for complex life to evolve and persist. There's a deep peace in this orbital stability, in knowing that the solar system is configured in a way that's been stable for billions of years, and will remain stable for billions more. The planets follow their appointed paths, perturbing each other slightly, but never dramatically, coexisting in a gravitational balance that has endured for most of the age of the universe. From planetary orbits, let's drift to the ancient star clusters that orbit in galaxies' halos. We discussed globular clusters earlier, but there are also dwarf galaxies, small satellite galaxies that orbit larger ones. The Milky Way has dozens of known satellite galaxies, small collections of stars bound together by gravity, orbiting our larger galaxy. The two largest are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches of light. These satellites have their own stars, their own gas, their own dark matter halos, but they're gradually being pulled apart by the Milky Way's gravity through tidal forces. Long streams of stars have been stripped from some satellites, trailing behind them in their orbits like cosmic debris. Over billions of years, many of these satellites will be completely disrupted, their stars joining the Milky Way's halo, their identities erased. But this disruption is slow and gentle. The satellites aren't destroyed violently. They're simply stretched by tidal forces over hundreds of millions or billions of years, gradually dispersing. It's galactic cannibalism, but peaceful cannibalism, taking eons to complete. And in the meantime, these satellites continue to orbit, their stars shining quietly, following their slow paths through the Milky Way's halo. Let's contemplate the patience of comets in the Oort cloud, that vast spherical shell of icy bodies surrounding the solar system. The Oort cloud extends from perhaps a few thousand astronomical units from the Sun to nearly halfway to the nearest star, about 1 light-year or more. It contains billions or perhaps trillions of comets, icy bodies left over from the solar system's formation, gravitationally bound to the Sun, but barely, orbiting so far out that their periods are measured in millions of years. Most of these comets have been orbiting in the Oort cloud for the entire 4.5 billion year history of the solar system. They're pristine samples of the solar nebula, frozen in time, unchanged since they formed. They orbit in darkness, never warmed by the Sun, which from their distance is just the brightest star in the sky, no different from other stars except for being slightly brighter. Occasionally, a gravitational perturbation from a passing star or giant molecular cloud nudges a comet's orbit, sending it falling toward the inner solar system. These long-period comets take thousands or millions of years to complete their journey inward. As they approach the Sun, they warm up, their ices sublimate, creating the characteristic comet tail. After passing the Sun, they head back out toward the Oort cloud, perhaps to return in thousands or millions of years, or perhaps to be perturbed again and ejected from the solar system entirely. But most Oort cloud comets will never visit the inner solar system. They'll remain in the outer darkness forever, slowly orbiting, patient and cold, witnesses to the solar system's entire history, but never participating in its inner drama. There's a serene isolation to this existence, floating in the darkness at the edge of the Sun's influence, barely bound, but bound nonetheless, eternally part of the solar system, but forever separated from its center. From the Oort cloud, let's consider the deep silence of space. Sound requires a medium to travel through, air or water or some other substance that can support pressure waves. But space, being nearly a vacuum, cannot transmit sound. No matter how energetic an event in space might be, it occurs in silence. Supernova explosions, colliding galaxies, quasars emitting the energy of billions of suns, All of these happen without making any sound. This silence is profound and absolute. If you could somehow survive in space without a protective suit, you'd hear nothing except perhaps the sounds of your own body, your heartbeat and breathing, and the creak of your joints. But from outside, nothing. The universe in all its grandeur and violence operates in complete silence. This silence might seem eerie or unsettling, but it's also peaceful. There's no cosmic noise, no background hum or roar. Just silence, pure and complete. Radio waves and other forms of electromagnetic radiation carry information through space, but they're not sound. They're oscillating electric and magnetic fields that can be converted to sound if we choose, but they don't make sound inherently. The silence of space is a reminder that our experience of the universe is mediated by our senses and instruments. What we call sound is just pressure waves detected by our ears. Radio waves are just oscillating fields detected by our instruments. The universe doesn't inherently have these qualities. It simply is, and we interpret it through whatever means we have available. Let's think about the patience required for interstellar travel. The fastest spacecraft humans have ever launched is the Parker Solar Probe, which reached speeds of over 160 kilometers per second. At that speed, it would still take more than 7,000 years to reach the nearest star, Proxima Centauri, and that's only if we could somehow aim it in that direction and maintain that speed outside the sun's gravitational influence. More realistic estimates for interstellar probes suggest journey times of tens of thousands or even hundreds of thousands of years to reach the nearest stars. The Voyager spacecraft, launched in 1977 and now in interstellar space, won't come close to another star for about 40,000 years. These timescales are so long that no human mission could hope to see results. We could launch a probe today, and it would arrive at its destination thousands of years after our civilization has changed beyond recognition or perhaps ceased to exist. This enforced patience, this necessity of thinking in terms of thousands or millions of years for interstellar exploration, is actually quite peaceful when you think about it. The universe is not in a hurry. The stars will be there whenever we're ready to visit them, if we ever are. There's no rush, no deadline, no urgency. Space travel at the speeds available to us requires us to think on cosmic timescales, to plan for futures we'll never see, to be content with processes that extend far beyond individual human lifetimes. Let's consider the gentle warming of the universe by starlight. Every star emits light and heat that radiates into space. Most of this radiation travels forever through the expanding universe, never being absorbed by anything, just spreading outward and becoming more diluted as space expands. But some radiation is absorbed by dust, by gas, by planets, warming them slightly. Over billions of years, the cumulative effect of all starlight has slightly warmed a universe above what it would be from the cosmic microwave background alone. This warming is tiny, perhaps equivalent to raising the average temperature by a fraction of a degree, but it's real and measurable. The universe is slightly warmer because stars have been shining. There's something pleasant about this thought, that all the stars and all the galaxies are collectively warming the universe, adding their tiny contributions to the cosmic energy budget. It's a gentle, persistent effect, accumulating over eons, a subtle transformation of the cosmos by the presence of stellar light. From warming, let's drift to the cooling of remnants. White dwarfs, the remnants of sun-like stars, are born hot with surface temperatures of tens of thousands or even hundreds of thousands of Kelvin. But they have no internal heat source, no fusion reactions to maintain their temperature. They simply radiate away their residual heat into space, gradually cooling over billions of years. The coolest white dwarfs observed have temperatures of a few thousand Kelvin, having cooled for billions of years. Eventually, given enough time, they'll cool to room temperature and below, becoming black dwarfs, cold, dark remnants of long-dead stars. But the universe isn't old enough yet for any white dwarf to have cooled completely to a black dwarf. The process takes trillions of years, far longer than the current age of the universe. This slow cooling is one of the most patient processes in the cosmos. White dwarfs don't do anything except cool. They don't evolve, don't change composition, don't interact with much of anything. They just sit there, or rather orbit through space, gradually radiating their heat into the void, becoming cooler and dimmer over timescales that dwarf human comprehension. It's an extremely long goodbye, a stellar remnant slowly fading from view, taking longer to cool than it took to live. Let's contemplate the idea of cosmic recycling, the way matter and energy are constantly being transformed, but never created or destroyed, following conservation laws that are among the most fundamental in physics. Atoms that were once in a star can later be in a planet. Atoms that were once in a planet can be ejected into space by an impact and later incorporated into another planet around another star. Your atoms have been recycled countless times. They've been in stars and interstellar gas clouds, in the solar nebula, in Earth's early molten state, in ancient oceans and extinct organisms, in rocks and air and water, and now temporarily in you. Eventually they'll leave your body, returning to the environment, to be incorporated into other living things, other minerals, perhaps eventually to be part of Earth's atmosphere or oceans, and on some unimaginably distant timescale, perhaps to return to space and join future stellar systems. This recycling is endless and universal. The universe doesn't create new matter or energy in meaningful amounts. It just rearranges what already exists, transforming it endlessly, creating new configurations, new structures, new complexities, but always using the same building blocks. We're all made of recycled material, and our atoms will be recycled after us, participating in the ongoing story of the cosmos long after our brief moment of consciousness has ended. There's something deeply peaceful about being part of this cycle, about knowing that you're not separate from the universe, but part of its ongoing transformation, a temporary arrangement of atoms that will eventually rejoin the cosmic flow and become something else. Death is not an end, but a transition, a return of borrowed atoms to the general pool, making them available for future uses, future forms, future possibilities. Let's think about the patience of scientific discovery itself. Astronomy is largely an observational science. We can't experiment on stars or galaxies. We can only observe them and try to understand what we see. This requires patience because astronomical phenomena often unfold slowly. A star might take millions of years to evolve noticeably. Galaxies take billions of years to change significantly. But even on shorter timescales, astronomical research requires patience. Building a major telescope takes years or decades. Analyzing data from observations takes months or years. Developing theories and testing them takes careers, sometimes multiple careers, as ideas are refined and improved over generations. The pace of astronomy is necessarily slow because the objects of study are so distant and their changes so gradual. This enforced patience is actually quite healthy. It prevents rushing to conclusions. It encourages careful thought and thorough analysis. It reminds us that understanding the universe is a long-term project, not something that can be hurried or forced. The cosmos has been here for nearly 14 billion years. It will be here for trillions more. We can take our time to understand it. And finally, let's contemplate the ultimate peaceful truth about the cosmos. It simply exists, without need for justification or purpose, without requiring our understanding or approval. The universe doesn't care whether we comprehend it or not. It doesn't need us to observe it or study it or appreciate it. It just is, following physical laws, evolving according to deterministic and probabilistic processes, creating structure and complexity where conditions allow. Before we conclude this journey through the most relaxing aspects of space, let me share a few more gentle observations, peaceful truths about the cosmos that can calm your mind and prepare you for deep rest. Think about the predictability of celestial mechanics. The planets orbit according to precise mathematical laws discovered by Kepler and explained by Newton. These laws are so reliable that we can calculate planetary positions thousands of years into the past or future with extraordinary accuracy. Ancient astronomers used this predictability to create calendars and predict eclipses. Modern astronomers use it to plan space missions and study orbital dynamics. This predictability provides a kind of cosmic stability. The universe might be vast and complex, but it's not capricious or random. It follows rules, and those rules are consistent and knowable. When you look up at the night sky, you're seeing the result of deterministic processes operating according to eternal laws. Tomorrow night, the stars will be in slightly different positions due to Earth's rotation and orbit, but you can calculate exactly where they'll be. Next year, same thing. 1,000 years from now, same thing. There's profound peace in this reliability. The cosmos can be trusted to behave consistently. The sun will rise tomorrow. The moon will go through its phases. The seasons will cycle. The planets will continue their orbits. This constancy provides a stable background against which our temporary lives play out. Let's think about the abundance of second chances in the universe. When stars die, they don't simply cease to exist. They transform, returning their material to space, where it can form new stars and planets. When planets are destroyed by impacts or tidal forces, their material doesn't vanish. It disperses and eventually becomes part of other worlds. When molecules are broken apart by radiation, their constituent atoms can form new molecules. The universe is constantly recycling and repurposing. Nothing is truly lost. Everything transforms into something else. This applies even to energy. It cannot be created or destroyed, only converted from one form to another. The light from a distant star might be absorbed by your eye, its energy converted into neural signals, contributing infinitesimally to your perception and consciousness. That energy came from fusion reactions in a star, converted from mass according to Einstein's equation, traveled across space for years or centuries, and ended up contributing to your experience. Every atom in your body has been through countless transformations before becoming part of you, and will go through countless more after you're gone. You're a temporary arrangement, but the atoms themselves are ancient, having existed since shortly after the Big Bang, and will continue to exist for as long as the universe does, which might be forever. Consider the gentle giants of the cosmos, the supergiant stars that dwarf our sun. Betelgeuse, the bright red star in Orion's shoulder, is about 700 to 900 times the diameter of the sun. If placed at the center of our solar system, its surface would extend past the orbit of Mars. Ooey Scutty, one of the largest known stars, is perhaps 1,700 times the sun's diameter, large enough to englobe the orbit of Saturn. These stars are so large that their surface gravity is quite weak despite their enormous mass. The outer layers are barely bound to the star, and stellar winds constantly blow material off into space. This mass loss is gentle and continuous, gradually dispersing the star's outer envelope over millions of years. Eventually, the star will shed so much mass that only the core remains, which might explode as a supernova, or might simply collapse into a compact remnant. But during their lifetime, these giants are peaceful, stately objects, shining steadily despite their immense size and power. They represent the universe's capacity to create structures of extraordinary scale, to organize vast amounts of matter into coherent objects that persist for millions of years. And when they die, they contribute enriched material to the galaxy, seeding future generations of stars with the heavy elements they've created. Let's contemplate the empty spaces in atomic structure. Atoms are mostly empty space. If an atom were scaled up to the size of a football stadium, the nucleus would be smaller than a marble at the center, and the electrons would be tiny specks orbiting in the outermost seats. The vast majority of the stadium, corresponding to the space between the nucleus and the electrons, would be empty. This means you're mostly empty space. The solid feeling matter of your body is actually mostly emptiness, with tiny particles separated by relatively vast distances. The reason you feel solid is because of electromagnetic forces between electrons in your atoms and electrons in other atoms. When you touch something, you're not really touching it in the sense of atoms making contact. You're feeling the electromagnetic repulsion between electron clouds. This emptiness at the heart of matter is both strange and calming. It means the universe is more spacious than it appears. It means solidity is an illusion created by forces rather than by actual contact between particles. It means there's room for complexity and structure, even within what appears to be solid matter. The space within atoms allows for the quantum behavior that makes chemistry possible, that allows for the diversity of materials and molecules that make up the rich complexity of the universe. From atomic emptiness, let's drift to the peacefulness of stable isotopes. Most atoms in the universe are stable, meaning they don't undergo radioactive decay. They persist indefinitely, maintaining their identity for the lifetime of the universe. Hydrogen-1, the most common isotope of hydrogen, is stable. Carbon-12, making up most of the carbon in your body, is stable. Oxygen-16, most of the oxygen you breathe, is stable. These stable isotopes make up the bulk of ordinary matter. The radioactive isotopes, the ones that decay over time, are comparatively rare. This is fortunate because it means most matter is stable, persisting indefinitely, providing a reliable foundation for structures like stars, planets, and living things. If most isotopes were radioactive, the universe would be a much more chaotic place, with atoms constantly transforming into other elements, making stable structures difficult to maintain. The existence of stable isotopes is a consequence of nuclear physics, of the balance between the strong nuclear force binding protons and neutrons together and the electromagnetic force pushing protons apart. Some configurations are stable, able to persist indefinitely. Others are unstable, eventually decaying into more stable forms. But the fact that stable configurations exist at all is essential for the universe as we know it. Let's think about the calmness of gravitational potential energy. When an object is high above a massive body, it has gravitational potential energy that can be converted to kinetic energy if the object falls. But this conversion doesn't have to happen quickly. The object can remain at a high position indefinitely, its potential energy stored, waiting to be released if and when the object falls. This stored energy is everywhere in the universe. Comets in the Oort cloud have enormous gravitational potential energy relative to the Sun. They could fall inward and release that energy as kinetic energy, but most will remain where they are for billions of years, their potential energy unrealized. Galaxies and galaxy clusters have potential energy relative to each other. They could fall together and merge, but many will remain separate for billions of years. This unrealized potential is peaceful. It represents possibilities that might or might not be actualized, energy that's present but not manifest, futures that could occur but haven't yet. The universe is full of such potential, both literal gravitational potential and metaphorical potential for change and evolution. Some of it will be realized, some won't, but it's there, waiting, patient, requiring nothing. Consider the democratic nature of physical laws. They apply equally to all matter, all energy, everywhere in the universe. An electron on Earth behaves the same way as an electron in a distant galaxy. Gravity works the same way in the Andromeda galaxy as it does here. Light travels at the same speed everywhere. This universality is extraordinary when you think about it. The universe could have been arbitrary with different rules in different places, but it's not. The same laws govern everything, everywhere, at all times as far as we can tell. This universality makes the universe comprehensible. If laws varied from place to place, we couldn't learn much about distant regions. But because laws are universal, we can observe distant galaxies and understand what we're seeing based on physical principles we've learned here. We can study the early universe through observations of distant light and understand what was happening based on laws that still operate today. The universality of physics is what makes cosmology possible as a science. From universality, let's turn to the gentle influence of pressure in space. Pressure is force per unit area, and it can exist even in the near vacuum of space. The solar wind, a stream of charged particles from the sun, exerts pressure on anything it encounters. This pressure is tiny, but over large areas and long times it can have significant effects. Comet tails point away from the sun, partly because of radiation pressure, and partly because of solar wind pressure pushing on the gas and dust ejected from the comet. Solar sails proposed spacecraft that would use large reflective sails to catch sunlight, rely on radiation pressure for propulsion. The pressure is minuscule, but it's constant and requires no fuel, allowing spacecraft to gradually accelerate over months or years to high speeds. Even the pressure inside stars is a gentle phenomenon in a sense. The core of the sun has enormous pressure, millions of times atmospheric pressure on Earth, but this pressure develops gradually over the sun's radius. It's not a sudden compression, but a smooth gradient, increasing steadily from the surface to the core. This pressure is what supports the sun against its own gravity, maintaining equilibrium, allowing the sun to shine steadily for billions of years. Let's contemplate the patience of chemical evolution. After the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. All other elements have been created since then through nuclear processes in stars. This chemical enrichment has been gradual, taking billions of years, with each generation of stars adding slightly more heavy elements to the interstellar medium. The first stars contained only primordial elements. The second generation had slight amounts of heavier elements created by the first generation. Our Sun, formed about 4.5 billion years ago, contains about 2% of elements heavier than helium, accumulated from previous stellar generations. Future generations of stars will have even higher metallicities as enrichment continues. This gradual process means the universe is slowly becoming more chemically diverse and complex. The diversity of matter we see today, the 100 or so elements in the periodic table, and countless molecules and compounds made from them. This diversity developed over cosmic history through patient stellar nucleosynthesis and dispersal. We're living in a chemically richer universe than existed billions of years ago, and future epochs will be richer still. From chemical evolution, let's drift to the peacefulness of darkness itself. Most of the universe is dark, either because it's empty space far from any light source or because it's occupied dark matter that doesn't interact with light. This darkness is not threatening or ominous. It's simply the natural state of space in the absence of luminous objects. Darkness allows us to see. If space were filled with glowing gas, we wouldn't be able to see distant stars and galaxies. They'd be obscured by foreground emission. But because space is mostly dark and transparent, light can travel immense distances, allowing us to observe the universe in great depth. The darkness is a feature, not a bug, essential for astronomy and for appreciating the cosmos. Darkness also provides contrast for the light that does exist. Stars shine brightly against the dark background of space. Galaxies stand out as islands of light in cosmic darkness. This contrast makes the universe visually striking, creating the dramatic vistas we see in astronomical images. Without darkness, there would be no such beauty, no such stark distinction between luminous and non-luminous regions. Let's think about the gentle erosion of surfaces in space. Cosmic dust and particles constantly bombard planets, moons, and asteroids, gradually eroding their surfaces. This erosion is extremely slow, removing perhaps micrometers or millimeters of material over millions of years. But over geological timescales, it can significantly alter landscapes. On the Moon, micrometeorite impacts have ground the surface into fine powder, creating the lunar regolith that astronauts walked on. On asteroids, this slow erosion gradually wears down features and smooths rough surfaces. It's a process of cosmic sandblasting, patient and persistent, operating continuously over billions of years. This erosion is yet another example of the universe's patience, its willingness to accomplish through slow accumulation what cannot be done quickly. Surfaces that appear eternal are actually slowly changing, being worn down grain by grain, transformed over timescales that dwarf human civilization. Nothing in the cosmos is truly permanent. Everything evolves, even if the evolution is imperceptibly slow. Finally, let's contemplate the profound peace of entropy's eventual victory. The second law of thermodynamics tells us that entropy, a measure of disorder, tends to increase in closed systems. Over time, energy becomes more dispersed, temperature differences smooth out, and the universe approaches a state of maximum entropy called heat death. This might sound depressing, but it's actually peaceful. It means the universe is heading toward a final state of equilibrium, a state of perfect balance where nothing interesting happens anymore because all energy is evenly distributed and no work can be extracted. This heat death is trillions upon trillions of years in the future, unimaginably far away, but it represents a kind of ultimate peace, a final rest for the cosmos after eons of activity. In the meantime, we're living in a time when the universe is far from equilibrium, when stars are shining, when planets exist, when life and consciousness are possible. These are temporary phenomena, existing because the universe hasn't reached equilibrium yet. Eventually, all stars will burn out, all black holes will evaporate, and the universe will settle into its final state of uniform emptiness. But that's so far in the future that it's barely worth contemplating. For now, we exist in an interesting time, and we can appreciate the fact that our existence is part of the universe's long journey toward eventual equilibrium. And with that final contemplation, having explored the most peaceful and relaxing aspects of space, having drifted through calm phenomena and patient processes, it's truly time now to rest. My voice fades away. The brown noise begins. Let it carry you into deep, restful sleep, into peaceful darkness, into the quiet restoration your body and mind need. You've journeyed through the cosmos tonight, discovering its serene side, and now you rest, part of the peaceful universe held by existence itself. Sleep well, sleep deeply. The most relaxing space stories have been shared. Now comes the most relaxing sleep. Good night.